Good morning. My name is Abdallah. I am a doctor from the University of Blida. First of all, I would like to thank the committee for accepting the paper entitled Enhanced PSOEU Algorithm to solve the optimal power flow problem for a deregulated power system. The outline of the paper is structured as follows. First, introduction, then problem definition, proposed PSOEU algorithm, case study, finally discussion and conclusion. Optimal power flow is one of the most important problems to solve in the power system community. The purpose of the optimal power flow is to minimize the fuel cost of generation and maintain a desirable system performance in terms of limits on the real power active, reactive power, magnitudes and angles in the bus voltages. Nowadays, the optimal power flow with environmental constraints domain is one of the most important search area in electrical power system field. With the increase in energy demand, the emission of polluting gases like nitrogen oxides have caused global warming. However, considering the valve point effect in the optimal power flow problem is another topic of interest. This paper proposes a novel algorithm combining particle swarm optimization and invasive weed optimization methods for the optimal power flow problem. Problem definition. The problem can be mathematically modeled as minimum function subject to the function g equal to 0, the function h inferior or equal to 0, where the function g is the load flow equation, function h is the system operation constraints, x and u are the vector of the state variables and the control, respectively. The objective functions. In this paper, we have taken into consideration three objective functions. First, quadratic fuel cost. The fuel cost function is modeled by the following equation. Second, fuel cost with valve point effect. The valve point effect function is modeled by the following equation. Third, emission. The objective function is to minimize the total emission of all thermal units using the following equation. System constraints. First, equality constraints. They represent the typical load flow equations as follows. Second, inequality constraints. They represent the active and reactive power injection, the voltage and transformers. Proposed PSOEU algorithm. For a better solution quality, the two algorithms are combined, in which PSO offers well throughout guided movements for each iteration, and EU algorithm offers good exploration. This choice allows to avoid some drawbacks, such as being trapped in local optima or converging to global optima in a long time. Case study. To validate the performance of the proposed algorithm, the 30, the 57, and the 118 bus standard networks have been used. Several objective functions are minimized, namely the fuel cost, the real power losses, the fuel cost with valve point effect, and emission. For the first case study, the optimal results of the 30 bus network are compared with hybrid PSO algorithm, sequential quadratic programming algorithm, and differential evolution, reported in the literature. Case 2. Fuel cost with valve point effect minimization. This case aims to minimize the total fuel cost of the generators under the valve point effects. The proposed PSOEU algorithm is compared with another algorithms. After 30 iterations, the optimal results are given as shown in the table 2. Case 3. Emission minimization. The fuel emission is chosen as the objective function for the minimization. The best results are listed in the table 3. For the 3 cases study, the PSOEU algorithm was able to converge in less than 40 iterations, as shown in the figure 2, 3, and 4. In this paper, a new intelligent method is proposed to solve the optimal power flow problem. The proposed PSOEU approach has been successfully applied to several objective functions. The approach was tested on different bus systems. Through the several cases study, it has shown that the proposed algorithm is good in terms of accuracy and effectiveness. Since it was compared with various different methods reported in the literature.